Hello everyone, I'm MD Omar Farooq Rokon. I will present SourceFinder, finding malware source code from publicly available repositories in GitHub. So the problem is how can we find malware source code? Because researchers need malware source code. So here is the opportunity. If you look at GitHub, you will find lots of public repositories that have malware source code. But the challenge is how do you find them? So for our org, input is GitHub with more than 32 million public repositories, and our desired output is malware source code repositories. So our key contribution is we are providing a systematic approach to identify malware with 89% precision, and we also got 7.5K malware source code repositories. And we are also providing a curated data set with 250 malware source code repositories. We also studied patterns and trends of these malware source code repositories. The main motivation behind our org is there is a scarcity of malware source code, and security researchers need source code to study malware behaviors and their techniques. So we also need malware source code to evaluate different security methods and tools. Um, there is a need for ground truth for reverse engineering, and uh, there is no available benchmark data set for malware source code, but there are lots of database of malware binary. So we need a database of malware source code. This is the roadmap of our presentation. Let's go into the related work. Uh, Unfortunately, there is no systematic study yet to find malware source code in the wild, but there are some studies that uses few malware source code derived from GitHub, and there are some archives. Mostly, they have malware binaries like the zoo and the virus total, and there are some studies that do binary to source code conversion, but even if they can convert the malware binary to source code, these are not actual source code. So we need actual malware source code. Next, we will dive into the collection. How do we collect these repositories from GitHub? So what is a GitHub repository? GitHub repository is just like a software project. Here you will have the source code of the repositories, and there are some files and data set, and there are some um, readme file where usually the author of the repository give the instruction how to run this project. So basically, we can say that a repository has two types of data: textual data and metadata. In the textual data, we have repository title, description, topics, readme text, and other files. And in the metadata, we have the date of creation and date of modification, number of forks, number of stars, number of bosses, and the followers of the author. So how can we collect these repositories? GitHub has over 32 million public repositories. So this is huge. But we can process this much data set. So how do we get malware candidates? To get the malware related repositories, we use some keywords that are related to malware. At first, we start with the keyword set Q1, where the keyword only malware. Then we have increased this number to 50, and then we have increased to 37 and named as Q50 and Q137. These keyword set are from three categories. The first category is malware and security related keywords. And the second category is malware family or malware types. And we have also added popular malware names into this keyword set. So how do we collect these repositories? So we search with these keywords set in GitHub with the GitHub search API. And for each repository, we collect and store repository specific information and author specific information. And we have also downloaded the project folder. And for each keyword set, we have got RD on for keyword set Q1. We have collected 2,700 repositories, and for keyword set Q50, we have collected 14,000 repositories, and for keyword set Q137, we have collected 97,000 repositories. However, there are some practical challenges for the GitHub API. A query returns only maximum 1,000 repositories. For example, the keyword malware match with more than 7,000 repositories. However, GitHub API will not let you get all the repositories. So we tried to solve this limitation by using the filter option of the API with the best match with the uh, most number of forks, with the least number of forks, with the most number of stars, least number of stars, like this. However, still we couldn't collect all those repositories that matched with the keyword, but we tried all the option to get as much as possible. Next, we will dive into the classification. How could we classify this repository into malware and benign repositories? So the overview of classification methodology is, at first we pre-process and clean the data that we collected from these repositories, and then we create the feature representation, because machine learning algorithm doesn't understand text or number. So we need to transform this data into a vector. So in order to do this, you use both bag of words and word embeddings with TF-IDF and normal term frequency. We have also used the pre-trained model of Google and Globe. Then we try to improve the effectiveness of our approach by selecting the most important feature, because GitHub has unstructured text, so there might be some unimportant or irrelevant words. So we try to improve this feature, and we if we do this, it will also increase the speed of our computation. And later we train ML model on this data set, and apply this model to classify the 97K repositories that we have collected in the previous step. And for this, we tried 7 different ML algorithms that we will see in the result section. And we have classified repositories into malware and benign. However, malware repositories may have both malware binary and malware source code, but our target is to get malware source code repositories. So in order to do that, we used a heuristic approach. The heuristic approach is, at first we will examine the extension of files in a malware repositories. And if a file has an extension of any programming language, we call this as a source file. And if a repo has a for example, if it is more than 75%, that means if the source file number of source file is more than 75% in a repositories, we call this as a source code repositories. However, in June 2020, GitHub labels repos as a source repositories. If there is a source code in a repositories, they label the programming language. So we uh, submitted our work before this. However, we try to validate our approach using the GitHub labeling, and it validates our approach with 100% precision. And now we will dive into the evaluation section. Mm, we evaluated all aspects of our approach. However, we will show some subset of this result here. Um, at first, we will see the which data field is the most important for work. Then we have uh, converted this data set into a feature representation. Then we did the feature selection. Then we selected the best model and evaluated the performance of that model and applied this model on the unlabeled repositories, that is 97K repositories, to classify them into malware and benign repositories. And finally, we identified source code in these malware repositories. However, this looks like a sequential approach, but these steps are mostly interdependent. So we tried lots of uh, uh, parameter and got the best value. At first, there is no ground truth for this work, so we need to manually create the ground truth. In order to do this, we invite 3 independent researchers. They were instructed to randomly pick 1,000 repositories from each repository dataset, that is from RD1, RD50, and RD137, and they remove duplicate and empty repositories, and then they carefully investigated these repositories to label malware or benign. And we kept only those repositories that are unanimously voted as malware or benign repositories. Following this step, we created 3 label dataset, LD137, LD50, and LD1, uh, with fairly balanced malware and benign repositories. However, as we have said in the data collection process, there are 2 types of data in GitHub repositories, textual and numerical data. But our observation with the experiment found that adding numerical feature actually decreases the accuracy by 3 to 5%. So from now we will say that data is just text textual data. That means title, description, topics, readme file, and other file names are our actual data of a repositories. Now we will see that which feature representation actually works better in our approach. So we tried both backup words and word embeddings, and we have found that backup words with TF and feature selection actually gives the best result. However, word embeddings with TF-IDF also give closer result. But if we use the feature selection with this improves by 6%. So we will use backup words with term frequency and feature selection from now on. And here the classification accuracy range seems like confusing, but the range means the best and worst accuracy of this 7 ML algorithm. This might be the naive bias and KNN. Now we will compare each of these machine learning algorithm for our data set, and we have found that naive bias shows better result with 89% precision and 86% recall and 87% FOM score, whereas there are some machine learning algorithm, that is logistic regression, KNN and LDA. They show higher precision with lower recall, but our target is to pick the model which keeps balance between the precision and recall. So we'll work with the naive Bayes model. And we are showing that our approach is robust to initial query set, because all these data set, um, we have got more than 89% precision. And for LD1 dataset, the precision is 98%. It's because for the query set Q1, there was just one word, malware. So all the repositories that are in LD1 are homogeneous. So they gives the best result. But in order to do this for all types of repositories, we will work with the LD137, as it was created from the 97K repositories, which has most number of or most varied keyword set, that is 137 keyword. Uh, Now we apply naive Bayes on the retrieve dataset, that is RD137. That means 97K repositories, and we have found 8.6K malware repositories, and rest are benign repositories. So we use our source code heuristic approach on these 8.6K malware repositories to identify malware source code repositories, and we have found 7.5K malware source code repositories. We further validated randomly picked 250 repositories. So our final result is we have got 7.5K malware source code repositories in 97K repositories. Later, we have done a large scale study on these malware source code repositories, and we studied the patterns and trends of these malware repositories. We have plotted the number of new malware repositories that are found in each year, and we found that it triples every 4 years. And in 2016, there is a big rise, and as we will see that ransomware were emerged in 2014 and gained momentum in 2017. However, if we see this and align this with the real world scenario, that in 2016 and 17 there was a worldwide attack of ransomware, so people tried to create this type of malware and upload it in GitHub. And we have also plotted the target platform of these repositories, and we have found that Windows and Linux are dominant in this list. However, these are also slowing down from 2017. So in the conclusion, we say that this is the opportunity that public archives like GitHub contains lots of malware repositories, and we propose a systematic approach to extract malware source code repositories from GitHub. We also provide a database of 7.5K malware source code repositories, where we have provided a curated dataset of 250 malware source code repositories. And we also studied the trends and patterns of these malware source code repositories. Thank you, everyone. If you have any question, you can email me